My name is Max Moser. Most of you know me from the backtrack distribution, and I'm working for a company called Dreamlight Technologies and do there some security research and testing. Well, I was thinking in the beginning, what should I do with that result? I mean, a customer was requesting some details about the insecurities or protection mechanism within those devices. And I was thinking, well, that's a nice target. No one did that in the past, at least not completely. And I just wanted to take a peek inside of it. And so I invested a lot of time on the first one. The second brand was then quite easy, but it was a way of losing nerves. During that analysis, I recognized that there is a lot of information on modulation, on binary encoding, decoding, but the whole process from starting with nothing to a complete understanding of your radio frequency-based transmission, it's quite interesting, and there are only a few public available documents which try to cover that on a reasonable level so that everyone can understand it, even if they are not that much into radio as I was in the beginning. So motivation, as I said, basically it was obvious that they are insecure, but everyone was consulting, well, you shouldn't use that, they tend to be insecure. The vendors told, well, we have some encryption, some said we have not, and so on. And so a customer were asking our company for taking a look into it. History. There are different types of wireless keyboards. The first generation basically was infrared based. They are popular still in hotel TV systems or in, let's say, near field transmission where you have direct on-site connection possibilities. Then the next generation was 27 megahertz base. That's most of the time in Europe, at least, it's that frequency. I heard that in US you have those 433 megahertz ISM band also freely available, so maybe there are some implementation on that part as well. And newest generation is based on 2.4 gigahertz transmission. This does not have to mean that this is Bluetooth, just because it's using the same frequency. But there are a lot of different vendors selling already Bluetooth-based keyboards. Expected operation, I guess that's pretty clear. The keyboard is communicating to the receiver, which is attached to the PC and transmitting keystrokes. Some fundamentals in the beginning. What is a keyboard? Basically, a keyboard holds a matrix which basically is interconnected to a microcontroller, which then sends the correct signal to the receiver. Depending on the implementation, they send not only the matrix values, they send standardized hit codes or scan codes, depending on the solution. The brands which I have in deeply analyzed is Logitech and Microsoft, and Microsoft was doing it using standard hit codes and some nice, much nicer protocol design related to how easily you can track with very few packets what keystrokes have been issued by the user. I will come back to that later on. So then you need a transmitter. That's normally something like that within the keyboard, and there is an antenna attached then, and they just take the signal and does the modulation onto the frequency and send it out to the air. Then you have a receiver that's depending on the brand and the age of the receiver, they have different implementation. It's quite interesting that Logitech, for example, did some very different looking, at least, layouts, but they still are backwards compatible, so that's quite interesting. And Microsoft here has a very simple and nice design for their receivers. The most important part here is that if you combine a keyboard with a specific host or receiver, you need somehow to store a value, and this value is basically stored in the receiver side, so that when you switch off the computer and you switch it back on, only that specific keyboard should be able to send keystrokes and communicate with the receiver. So we have to remind us that there has to be somehow a storage for saving which keyboard he was associated to. Basically, a receiver has a component of a microcontroller which handles the USB communication and does some depending on the implementation, does some modulation as well for the frequencies. In that Microsoft design, it looks like they are doing, most of the time, they are doing just the USB side, and there is an EEPROM for saving the latest associated keyboard, and there is a transceiver chip. It's quite interesting that this Texas Instruments chip is a transceiver, able to communicate in both ways, but they don't use both ways for communicating, at least until what I have seen during my analysis. For sure, there is a crystal for modulating and bringing to the right frequencies. Then at the end of the receiver and the computer, you have an operating system. That's very important to understand that the key mapping is not done by the receiver. It's done by the operating system. So you select your desired keyboard layout, like US, German, whatever. So there has to be some standard code transmitting the error, and then it's interpreted by the operating system. Also, key repeatings and delay rates are interchangeable in the operating system, so this is not a feature of the firmware of the receiver. Okay, now, because you can have multiple of those keyboards in one room, you need some way how to associate a specific keyboard to a specific computer. And this is somehow like a tuning process that only that keyboard can communicate to a specific receiver. If there is no procedure like that, one could see the keystrokes of the other one. And I remember back in the early days of wireless keyboards, there were some funny issues on that, but they have extended the number of possible keyboards, quite a few. Normally, that's just issued by pressing a connect button on the receiver side and one on the keyboard. You have there some little buttons. Usually it's labeled by connect, and then you have to push them both, and they seem to exchange something. Because you need a separation, they have to at least send somehow an identification from a keyboard to the receiver, because otherwise it would not be possible to separate two keyboards in one receiving range. Interesting in this area is that this is a pure one-way communication, so just the keyboard is sending to the receiver. So basically you bring the receiver to a specific state where it accepts the next keyboard sending the right packets. So what's wrong with that? Quite easy. If you take two receivers and you push the connect button on both and you push it on the keyboard as well, then both of them will get the same keyboard associated. So basically with just the same receiver within the receiving range, you can already receive keystrokes. That's well known already. In 2001, a German company posted that on Backtrack, that this is possible. The problem with that was that you had to be there when he pushes the connect button. You could enforce that by just sending noise to the frequency to cut the communication between the keyboard and the receiver. Yeah, basically that's it. So both of them get the synchronization information. We wanted more. we wanted to understand completely what is traveling there, and we wanted to see the keystrokes, and we wanted all of them at once. So if someone is using more than one keyboard, is it possible to read all of them, separate them, to bind it to a specific person, for example. And injecting keystrokes is very interesting. I will come back to that later on. And yeah, take over the world is maybe not the primary target. Yeah, basically what we started is a standard reverse engineering. First, information gathering. This was very quite interesting phase because there are hundreds of different implementations how to build a wireless keyboard, and there are so many different vendors and they look so different. Then we needed a way to identify the signal, and I will just step through the different areas. The data decoding binary analysis I will cover in one section. Basically just analyzes the signal, what is going on there, and some decryption when it was needed. Information, I just can say that the FCC is interesting for finding the right modulation types. Electronic data sheets are important if you have a chip labeling. It was very helpful. Patents are also sometimes helpful if you don't have any clue, but it's quite easy to find it without that. So if you got some information already collected, you try to get the signal. So there are basically two ways you can get it out of the air, or you can get it from the hardware, the issue itself. So from the air, it's quite easy. I mean, first you need to find the frequency, watch into the manual. That's the first advice. You will find it there often. If not, you will see that picture with the crystal. There is 26690. That's a different product. And they use that frequency, obviously. What you can do then is you can use a standard radio receiver, tune it to the specific frequency and get the signal. Or you can use a ordinary receiver of the product and just tap the signal like I did it in the picture. There are the signals from the different transmitter chips. So, and this was quite okay to analyze the signal straight from the air, but we wanted to eliminate any possible source of errors because we did not even know what we are looking at. So we decided to catch it directly on the originator, and that's basically a keyboard, just without the matrix and the keys. And yeah, we basically tapped it on the keyboard directly. Microsoft was gentle enough to label the pins. So there is a DA, which means, I guess, digital analog, but that's a wild guess. And in the next generation of keyboards, we found it directly on the microcontroller, where the pulse width modulation signal is emitted. I hope this is correct. So this allows us to getting the best possible signal before even thinking about looking how it looks like. And well, then I started different areas. I tried GNU radio for getting it directly off the waves, and I was stupid enough to not being able to write a proper decoder. So I was searching for a different way, and I come up with a very simple way to just tap my radio receiver before the amplifier to the headphone. So I got a very, let's say, noise-free or distortion-free signal, and then I just put on a cable and put it into a sound card to getting basically a very simple oscilloscope, or just getting the values of the signal I will get. So that's quite a simple solution, and it's quite effective, and yeah, we had good success. So again, you can take that signal directly from the receiver or from a better radio receiver. So next, well, we now have something like a sound, something like a signal. This sounds pretty strange. I can show it to you. Sounds like that's a T. And now we needed to find out what this means, basically for binary data, binary representation. And so there are basically some ways how to encode binary data onto a signal. I just collected now 3 examples. Non-return 0 is one, Miller and Manchester are the other 2. Those 3 are used in a lot of serial communication models. And every product I checked so far were using a variation of Miller encoding or the Miller standard itself. But in general, it's always the same technique. You need some states which represent 0 or 1. In non-return 0, it's quite easy. One state of the signal is 0, and the other one is 1. You can turn it around depending on how you define it. So that's extremely simple. Manchester, it's a bit different. If you change the state during one bit period, one time between one line and the other one, then depending on the interpretation, on the variation, you have either when it's going from high to low, you have a 1, or when you come up from low to high, then you have a 1. So it's all about transmission there. But in Manchester, you need a clock signal. That's an additional signal. And this was not there at the keyboards. So we were checking Miller encodings because they were used in a lot of different radio transmissions. And what you see down there is actually, I have other pictures then, a picture of just a recording of that signal you just heard. It wasn't a T, but basically the same. And the Miller encoding is all about, let's say, the time between the transitions. So it's pretty describing that you have 3 different states. You have a period of 1 between 2 transmissions. You have a double the length, a 2, and you have 1.5. And that's extremely characteristic for that Miller type of transmission. So you can immediately see it out of the picture that this will be for sure a Miller-based communication. So now we tried, when we were expecting that this is kind of a Miller code, we were looking still at the waveforms. That's how it looks like. We just connected the sound card with the signal, recorded in Audacity or any sound editor software, it will work. And we were first just looking at how it looks like. And as you can see, if I press 3 times nay on a Logitech keyboard, it looks something like that. So one can see that there are 3 something and a lot of noise in there. So we took one of those something and extended a bit into the view, and we see, okay, per keystroke we have 2 sections. Actually, depending on the version, you have 3 of them. That's just repeatings. And then we go additional a layer deeper and extended the view a bit. And then you could easily see that there are different sections. By just measuring how many samples are recording between one transmission to the other one, you can say it's a binary, it's a Miller period 1, 1.5, or 2. And now the special part is the start and the end are longer. So these are, depending on the implementation, 2.5 or 3 time periods longer. So this seems to be somehow separated because it is an illegal signal, basically, in terms of Miller encoding. So you can easily say that if you take that as a start and the other one as an end, so there must be data. And then I started just to overlay the pictures and see, okay, that's a 1-to-1 repeat at the end. So it was quite obvious already that they are transmitting 2 times the same data per keystroke without even knowing what's going on exactly. And for me, it was quite important to learn that you have to abstract it first if you don't know what you're looking at. So when we had that type and we know how it looks like, how the structure is, we wrote a small encoder and just said, okay, tag it as end, as a start, and then we used the Miller standard to get the binary representation of that 1, 1.5, and 2 thingy. And we collected just a few keystrokes from different keyboards, from different serial numbers, and so on. So what you get is basically something like that. This hurts your eyes quite a bit and could also be called as a big mess. And we had no clue what's going on. So in fact, in real life, this looks something like that. You print out, you measure, you count, you try different variations because then we changed it from 1, 1.5, and 2 to A, B, and C because it's easier to look at. It gets more colorful, and at the end it drives me somehow insane because they did not use the standard Miller encoding, so it was quite a hard time to find the proper way. And so I tried to fit that somehow together. Well, there is an indicator that it's wrong if the length of a binary stream, for example, a representation of 0 and 1 differs in length constantly. If you press A and you press A again, then it should at least have somehow the same length. So this is a quite good indicator. And if you have a lot of similar values, a lot of zeros or a lot of ones, that's obviously not that much possible that this is a meaningful number or value at the end. And if you see the expected clear text already in that binary representation, what you typed, for example, in A, then it's perfect. Then you got it already. So, but in normal life, this does not happen that you find it immediately. So you try to separate that big mass into blocks. There are different type of data block boundaries which are possible, 4-bit nibbles, 8-bit boundaries, 7-bit ASCII stuff. And so we were searching for boundaries inside those binary representation. One thing maybe it's interesting that if they transfer hit code or scan codes, they will be different in length. So we try to distinguish between those two. So in real life, this looks something like that. You take a big mass and just separate it by vision or by logic. And some are pretty obviously always where it changes, we just separate them. But this is just basically a representation, how it could look like. It wasn't the actual protocol. So in real life, this looked like that in the beginning. I was coloring using pencils and searching for stuff, and this was in fact a wrong variation I've tried. So you see some bytes are working quite well, and then they are completely messed over, different lengths and so on. So I wasted a lot of time on just finding the right variation of that Miller standard. So if you got some separation, you're looking for fixed values and for variable length values. Fixed values can help you to separate variable lengths, that's clear, and for finding, for example, static values like a keyboard ID, a vendor ID, which is always the same per keyboard or per vendor. So an example here for Logitech, I have 2 keyboards, and I just pressed some keys. And I just labeled it universal, static, and random. And universal means that on every keyboard I tried, I received the same results. I just go forward. So you can see there are some universal bits which are always, which are always the same. And then you had some static ones, which are static per keyboard. That's very important. So this seems to be like, well, we can distinguish keyboards already on that static port. Interesting is also that there where the question mark is, we have alternating 1 and a 0. I was pressing keys and releasing them. So this was kind of a interesting finding. Well, after that, it was quite simple. You take Logitech and just press key A down, key A up on keyboard 1, keyboard 2, and you will find that some parts will stay fixed. If you press key A independently, if it's key down or key up, you will get always that red value. So could this be an A? If you release the key, you will get always a 0, and if you press it, you will always get a 1. So it's extremely simple how they did that. I mean, that's basically it. I wasn't expecting it to be that easy on Logitech because I was first looking at Microsoft and it's more harder. So basically the talk for the Logitech part is over there. It's over here because now you just have to build a table depending on that values, which are red or violet depending on which key I pressed. So you end with something, I don't know what it is, protocol. Then you have something which looks like a keyboard ID, and you have a keystroke field. I know that those are too many bits already, but I don't care about it because I don't need it to just listen to them. And I have a key straight. On Microsoft, it looked quite a bit different. We had also some static parts per keyboard, and we had some universal parts. And you had some random parts, which are random even when pressing same key, auto connects and so on. I come to that a bit later, but in general you have something like an ID, I guess, that's the static part per keyboard, and you have some universal, I don't know, protocol or vendor, could be a possible field, and then I have some questions still in there. So on Logitech it was quite easy, making just a table, what button I pressed, what is the binary representation, that's it, that's enough for just reading it. But in the Microsoft implementation it wasn't that easy, so we had to find out, well, what's inside of that data and what's inside that random stuff we saw and in that part. So we were searching for values which are repeating depending on what key we press and depending on when we do what action. So basically what we could see when we just collected enough information, that there were some blocks, those are 16, and then in front of it there were already again 4 bits which are repeating every 16, let's call it steps. So there is a reason for that. If you look at a hit table, you can clearly see that between one hex representation of the hit code and one with a different digit in front of it is always 16 because it's a hex number. So we expect it to be that to be a hit code based transmission. But we were still not sure what it actually means. So we were searching for more known clear text and were analyzing the content of that EEPROM. I mean, the receiver has to store the associated keyboards, and so we tried to read it out, what's in there, and hopefully we find some clear text which we can look at in the binary representation. Yeah, basically we used bus sniffing just to read what it's going through to the EEPROM, and this was quite simple. And yes, during the synchronization process, the whole ID of the keyboards will be transmitted and wrote into the EEPROM and read it again. So we found some data and we just were searching for it. And so we compared the data we already have collected together with the moment when we changed the keyboard or we just pushed the connect button again. So I just step a bit over. You can always see that there seems to be a static ID which never changes. Then we did some tests, and at the end I wrote the labels that there seems to be some static numbers for the mouse, which is associated as well. Then we have some per keyboard static stuff, and we have some random stuff. And if you take a look at the arrows on the side, you can see that in the first line, we had a sync on keyboard 1 and a sync on mouse 1. On the second one, we had only synced the keyboard but not the mouse. So now you can search for static values between when is the mouse changing, when it's the mouse not changing. And I step down a bit because now it's a bit difficult. At the end, it's pretty obvious and colored. As we were progressing with the analysis, we found out that, okay, if you press the synchronization, some parts will change. You can see there the upper three were sync keyboard 1, then we changed to keyboard 2, so keyboard static number changes. And there is one important one, that one with the keyboard random part, that violet thing. You can see that we don't had a sync on keyboard 2 on that line. So if we don't push the connect button, we will have the same value at the random. So this was quite obvious. I mean, the static one, I think it's the vendor or a protocol specific thing. Mouse will just change if you synchronize the mouse. Then keyboard, if you change the keyboard or push connect again, you will get the same values. And the random changes every time you push the connect button. So that's the interesting part. So we can distinguish already between different keyboards. We can separate keystrokes coming from multiple keyboards depending on the static part of it, but still we don't have any clear text. So we have some ideas and so on, and we have separated some modules, but we don't get any correct keyboard scan codes or hit codes. So, well, some bytes were generated by pressing the connect button. The receiver stores them, and that's somehow important. And yeah, we tried just to think about it, and well, this sounds like weak encryption or obscuration or something like that, because we have some repeatings, and this couldn't be any good because that should not happen. So we were checking the manuals, and I was calling up the help desk, and it was quite interesting that that guy told me, well, read the Bluetooth white paper regarding encryption on 27 megahertz based products. That was quite interesting, but he was right. There is a part in there. Basically, if they do, it's proprietary, and that's somehow, let's say, meaningful statement, because I hadn't a clue afterwards. Logitech was more helpful. There was a wording like, if you like to activate encryption, then you have to do some fancy stuff like installing software and activating it. So I expected to be no encryption. What was the case, as we have seen earlier. So with that know-how, we go back to analysis and found, when we remember that picture, we tried the following. We pushed the character A, so pushed the A on the key, and we found out that, okay, the hit code, the USB standard hit code, is the value 04 in hex. A Q has 14, so basically just the one at the beginning is changing, so from 0 to 1, the 4 is still the same. So, and the A and B is just one value different, so the 0 in the front is identical. So now if you look at a binary level, there need to be some similarities, and in fact you can look at it. When we extract it from the binary transmission, we saw that just the nibble 1 part changes on the A and Q, and the rest is identical. And if we hit A and B, just the nibble 2 is changing. So yeah, this seems to be somehow a static encryption or whatever we call it. So this smells definitively like XOR, just a static key and doing some shiftings. And I'm sure that's not meant as a encryption per se, but maybe for additional separation of different keyboards. But so the next step was logically to just apply this and do an XOR on the hit codes and the collected information, and at the end we did it for the first part of the nibble and the second part, and so we get a possible key, binary key, and we tried that with another keystroke we have pressed. And in fact, this was the key, but we were asking then, well, where does this key come from? I mean, there are two possibilities. They have to transmit it over during pressing connect button, or it's a magic fixed vendor whatever key. And no, it wasn't that magic. It was that random fancy part, which changes every time you press a connect button. But funny is that not the whole random is used, just only very few bits there. So if you can listen to the connect press event, you got the key. But this means still that you have to wait for synchronization, and that's not cool. So, but we are able to get real hit codes out of that transmission, and so we are able to read basically what it's being typed. And so now we try to get rid out of that waiting for someone pressing the connect. There are different possibilities to achieve that. Brute force somehow is cool if you have FPGAs and stuff, and very useful, but in that situation it's just useless. And I mean, yeah, we tried it, and brute force is one way, but we were thinking, how can we predict known plain text for that communication when someone types in just regular emails or browsing the net and so on. And we thought about it, well, maybe this sucks as well, but let's try a simple word list. So www dot, for example, it's a very common word which everyone types on that keyboard somehow. So then we have known clear text, and we can get the key out of it. So this was in fact very effective. I was surprised how well, because first we thought about limiting key spaces and so on, and this was too simple. So, and now I have some demonstrations with me where I can show you how it actually works like, and then I guess we go for questions. Again, here's a simple radio receiver, just a cable to a USB sound card, because my Apple does not have a microphone in, so I had to use a USB thingy. I switch it on. That's quite annoying if you analyze a lot of keystrokes. So first, I go to Logitech ones. This application we wrote is basically just listening to the sound card and just then reading the values coming from the sound card and then try to decode data. Just let me check the sound source. Input, C media. Should work. So that's basically the Logitech keyboard, and in the beginning it tries to get up from his sleep mode, so it sends first some longer signal, and then because we found already the representation of the key, it's quite easy That's the right frequency. So we should be able to see it, but it's actually not working. Just let me start it again because I had the wrong sound source selected in the beginning. So now, dear Mr. President, I like to spend whatever. So as you can see, there is no receiver on my laptop and you can just press any keystrokes. So I have to say that Logitech is providing a software for Windows where you can activate encryption. I did not have the time to look at it, but it's somehow crazy. You have to press 2 buttons, then the keyboard knows that the next few keystrokes will be the key, and you have to type some keys which are represented on the screen, and then this needs to be somehow the encryption key. But the crazy thing is what's happening when I mistype during that time, I don't know. So I did not have the time to look at it, but I don't expect it to be that much difficult. Logitech also tried to push now a technology called Secure Connect, where they eliminate the needing of producing unique identifiers by just using RFID tags during packaging the keyboards. And I don't expect that they changed so much because, I mean, maybe they just shifted the ID generation process out of the firmware and just use that static one within the RFID chip, but will be maybe a next target, I don't know. But I did not have the time to look at it. So this was the easy one. And as a Swiss citizen, I have to admit that Microsoft solution was better. Even if Logitech is a Swiss company, or was a Swiss company, or whatever. So that's now the Microsoft Sniffer proof of concept. As you can at least read, we are just reading in some simple documents. And these are just a few common known words. And I try now to enter some keystrokes, and you will see basically in the beginning just, yeah, I have to change the frequency, sorry. By the way, Microsoft is using 1 channel, Logitech is using 2, but this does not differ. So in the beginning, you just see something like keystrokes. And that in the brackets is a keyboard identifier. And if he gets first time some keystrokes from that keyboard, he populates all possible keys. So there are not that many, as you can see. And now I type some words. Yeah, and then a window pops open, and because of my system, I have to enter this password once. And as you can see, there are the keystrokes I have just pressed. There are some errors. That's because I just brought my, let's say, crappy sound card with me with that bad antenna, and you simply don't get that quality. The sound card is really about $20, and so you have lots of problem with the signal. But as you can see, when I type now any further, it will show it in clear text. It's simply some Perl scripts again, which are reading it, and then we have separated interpretation, and we are generating log files so we can review it afterwards. And there is basically 1 key of those 2 possible which are used. And yeah, it's 1 byte basically, and so it's quite simple. And now for the second keyboard from Microsoft, I just press the connect button. And another window pops open. And as you can see, there is no key events already, but here in the back, maybe you can see it. the sniffer identifies a lot of sync packets. They send about 100, and I just said, well, after 60, say that's the right one, and just read out the key. And so you get the key out of it, and you have immediately the keystroke coming from that keyboard. So this is working right on. So the interesting part is, but it's quite difficult, that you can sniff basically both of them at the same time, but because they are using the same frequency, I have to type somehow slow, and it's not really usable, but as you can see, both are showing something. That's just, each one is interfering the other one because they are near to each other. So as you can see, let's switch back to presentation. I was asked about the range a lot of times. We had 10 meters using a copper wire of about 10 meters, because the frequency of 27 megahertz is about 11 meters something, I guess. So we had about 10 meters in the range through walls and doors. We were able to capture the signal from the upper floor, from the lower office. But I mean, the range is depending on your quality of receivers, on the quality of your antennas, and the quality of the programmer which does your code. And yeah, it's just depending on the imagination what you can get with a proper antenna. More to come. Yes, we are looking at the secure solutions at the moment. And we have made tests on replaying. Replaying is working on every keyboard. That's quite simple. You can record it using your, I don't know, tape recorder, and sending using a hand radio on the same frequency, and you will reproduce keystrokes, and you can collect information and decrypt it, for example, at home. But yeah, that's possible. Injection of custom-built packets is working, but the problem is that I have some unknown bits in the protocol of Microsoft at the moment, and so I have to brute force them, and so I just send more signal that it's actually needed to produce a single keystroke. But this is possible. So it's quite fun if you use Windows R and say, download my Trojan from the internet and please execute, and boost it over the whole city with 10 kilowatts of power, I don't know. Yeah, next is we'll build a commercial grade software to show that. And yeah, I mean, there is a nice thing about the firmware of the receivers. If we can modify the firmware at the location where it compares the keyboard ID to the stored one within the EEPROM, we can build a cheap sniffing device by just changing one comparison in the firmware to another one. So I guess we will be soon able to repam standard receivers. So, and then it's quite easy for everyone. So, questions? I guess that's 3 of them, which I can already answer. Oops. Okay. Yes, they are insecure. They are very insecure. No, there won't be a patch. I mean, you have to update the code inside of it. Interesting is that there is a transceiving chip, as far as I know. So you could at least do a two-way communication, but they don't do it. But I can also understand that this is a dying technology. I mean, there are Bluetooth keyboards, there are better transmitting types. So I don't think that will be fixed. And no, we don't release the tool at the moment. So, sorry? No, not at the moment, no. We had contact with vendors, and yeah, we had reactions, and I can understand that this won't be fixed at the moment. I mean, as I said, dying technology, not that much of a threat, but I insisted that it's not only a thing of 1 or 2 meters, just because it's stated in the manual that it works only 90 centimeters in range, so it's working through floors at least. So, yeah?
I don't know if you went over this at the very beginning, but I was curious what method are you using to process the audio into the binary? So you have
Yeah.
your waveform.
Yeah. Actually, we used an ordinary wave editor to look at it, and at the end I used lib sound file, I guess, for reading data directly from the audio port, and then I get basically raw values. I can define what type. So normally it's float, 32-bit, and I guess I used some 60-bit integer values, and then you get values from I don't know exactly, but depends on the type you choose. You get certain values, and then it's the most easiest part is to just type in some stuff and make some statistics of the value. So then you can say, okay, each sample he takes from that signal, he will just print out. That's the first step. So, and then you count how many times they had the same sample value. So then you can say how long was that signal if you take a look at the wave. And then you can say, okay, that's one period because it's very often there. And the next one is 1.5 because you can just simply count how many times the same or near the same sample is there. So it's basically really the same like a parsing an audio file. And this was quite amazing for me at the beginning because I'm not that much of a radio guy, actually. But yeah, basically it's just a simple audio processing. And there maybe one sentence I did not notice is just if you get a too strong signal out of your receiver, use a resistor in front of the sound card, and then it's perfect.
So that library is open source?
Yeah, it's open source. Yeah, or you can port audio is something also similar. Yeah, any audio library will do it because you just need the values. Any further questions? Yeah.
With Logitech, question for each vendor. With Logitech, did they make the encryption secure mechanism easy to find, and is it in the manual, or do you have to actually look for it? And is it obvious to find?
Well, there is a patent about secure transmission from Logitech, and this describes somehow how you could do something like that.
So I guess
But
the question is, you said that the vendor told you to type it.
Okay.
Is that in the manual, and can the user find that?
Well, that depends first on the salesperson you met. And second, there is an official paper about their Secure Connect improvements, and they told you a lot about the old stuff in the new white paper where they try to bring it to the market, the new solution. And so you know a lot of it just by that white paper. It's called something about Secure Connect white paper.
No, my question
So-
wasn't how to figure out about it. The question is, if the user buys a product
Hmm?
and he reads the manual,
Hmm?
okay, is it said in the manual?
That you have to optionally activate it. Yeah, it's written in the manual, but the software is not available for all platforms. So,
Microsoft has no equivalent functionality.
not to my knowledge. I tried their software and there was no type of possibilities.
So was Microsoft's reaction, I assume you've gone back to the vendors at this point in time and told them what you're capable of doing. Is Microsoft got something that they propose to deal with their 750,000 wireless keyboards that they sold?
Well, I was amazed how well they reacted to my posting to their email box, and they were cooperative to a certain level to help me on, for example, getting some numbers and so on. But they could not hand out everything. I mean, that's pretty clear. But there will be no quick fix. I mean, how should they do that? But maybe they will do something in the future. I don't know. But in the press, at least, there was a statement like, if we accept this as a problem, then we will do something. So I guess according to CNET, I guess what's the posting with the interview of somebody from Microsoft, they said, we will do something if this is really a problem. So, but I had some contact and they were pretty much gentle and helped me a lot, so I don't want to blame it on them. So, I mean, that, yeah.
I guess if you have a mouse in the area, a wireless mouse as well, it can be confusing. There must be some ID to figure out whether you're getting mouse traffic or keyboard traffic, right?
Now I have to think about it again. I'm not sure, straight out of the head, if Microsoft and Moser are using the same channel. I'm sure that all the keyboards are using the same frequency, but I'm not sure at the moment at the Mosers, because I just tested it during that sync process because it wasn't valuable for me during that research. If they use the same frequency, then they disturb that information. But I mean, this should be handled by protocol. But yeah, I don't want to guess, but I think they use a different frequency. But as I said, it's a guess. I don't know it. We can try it if someone has a mice and we can check the frequency, so that's okay.
Do you have any idea how many possible frequency channels there are for a keyboard?
Well, I have tried now Logitech, BenQ, Fujitsu, and Microsoft and Logitech, and Logitech and Microsoft are using 3, Logitech 2, and which are changing every time when you press the connect button, it takes the other one. So, and Microsoft is using for all their keyboard of the similar series, 1 single frequency. So.
You have multiple keyboards at the same.
Yeah, I mean that's the amount of static ID per keyboard, and well, I guess early documents told about 4,000 differences, but at the moment, I guess the marketing product talked about 60,000. And yeah, we just had to check the protocol again, and then I can say it for sure. But there are a lot, and I mean, I guess that this XOR feature is basically just for ensuring, again, that you don't see other keystrokes, or you at least see a wrong one if you get one from another keyboard. I don't really think that this was designed as an encryption. I mean. Okay. So I'm right on time then. Thank you.